All right, everyone. Now let's move on to Chapter 2, Essential Chemistry of Biology. Tracing life down to the chemical level. So a lot of people ask, why do we look at chemistry if we are studying biology? Well, everything that happens in biology is because of the chemistry of molecules, molecules of life, how they function. And so we need a general understanding of chemistry to understand biology. So biology includes the study of life at many levels. In order to understand life, we can start at the macroscopic level, which is the ecosystem, and work our way down to the microscopic level of cells. But here we're going to start at the microscopic level because we're talking about chemistry in this chapter. Alrighty, so let's look at this biological system, for example. We see all of these antelopes at a watering hole. So chemistry would provide us with answers like, why do they drink? Why are they thirsty? And this is all based on little chemical molecules and all of that good stuff that we're going to be talking about today. Alright, so now let's talk about matter. So matter is anything that occupies space and has mass. It's found on Earth in 3 physical states. So we all know these: solids, liquids, and gases. So when we talk about matter, we're talking about mass. So if you were on the moon, your mass would be the same as here on Earth. However, your weight would be different, but we're not talking about weight. We're just talking about mass here. So with solids, we have a definite volume and shape. With molecules that have specific structure. With liquids, so with solids, you always think about a block, a solid block. It's always going to have the same volume. It's always going to have the same shape. It is a solid wooden block. With liquids, they have a definite volume, but they have indefinite shape. So they change to fill different containers, as we all know. And then gas has indefinite volume and indefinite shape. So if an empty plastic bottle, so you have an empty plastic bottle, let's say that, it's actually not empty, it's filled with air molecules, which is a really good optimistic viewpoint on everything. Is the bottle half full? Well, the bottle is actually always full, because if it's not full with liquid, it will be full of gas. So anyways, empty plastic bottle, it's filled with air molecules. So now they have this, it has this volume and this shape of being in this plastic bottle. Well, you squeeze that bottle, and now it decreases its volume, and it changes the shape of the gas, right? All right, everybody understands that. I hope, anyway. All right, so let's move on. Elements are substances that cannot be broken down into other substances. And matter is composed of all of these. There are 92 naturally occurring elements on Earth, and we're going to look at these at this periodic table. So when you look at this periodic table, you notice that all of these elements are arranged in a specific order. And they're arranged by the atomic number, right here. So this would have, hydrogen would have an atomic number of 1, helium 2, lithium 3, 4, 5, and then we get to carbon, which is 6. The atomic number is telling you how many protons are in that atom. The element symbol, or in the element, sorry. The atomic number tells you how many protons are in this element. So in carbon, which our element symbol is C for carbon, we have 6 protons. And then we have this mass number down here, and all the mass number is telling us is how many protons and neutrons are in this element. The mass number is also called atomic mass. So you'll hear it referred to as atomic mass and as mass number. Or, yes, yeah, atomic mass, mass number. All right. So these are 25 elements essential to life, and they are actually essential. If we did not have them, we would die. These lower levels down here are called trace elements. They occur in smaller amounts. And these other ones, carbon, oxygen, hydrogen, nitrogen, make up 96% of the weight of the human body. Look how much oxygen takes up. That's ridiculous, 65%. All of these are important to life, including these trace elements. Without them, we would have problems sending electrical signals. We'd have problems maintaining a normal number of solutes, which means things dissolved. So all of these 25 elements are very essential to our well-being. Elements can combine to form compounds. These compounds contain 2 or more elements. So that's it. So example is salt, NaCl, that has sodium, which is Na, and chlorine, which is Cl. Together it's sodium chloride. We have H2O, which is water, and then we have C6H12O6, which is glucose, or a simple sugar. Let's look at what the smallest level of each element is. Each element can be broken down into all of its parts, and that would be called an atom. In this atom, we have a middle, which is the nucleus. So here's the atom, here's the nucleus. And in the nucleus, we have protons, which are positive. We have neutrons, which are neutral. And these are pretty easy to remember: pro, positive, neutral, and then we have electrons, which are negative. So electrons, it's not really an easy way to remember them, just protons, positive, neutrons, neutral, and then just remember that electrons are the negative ones. This is a very small scale of an atom. In a regular sized, well, an atom is small scale, so size is relative here, but in a 2-scale model, the electrons would be way further out, not that close to the nucleus. So let's get more into those subatomic particles. A proton is relatively large and positively charged. It's large and in charge. And an electron is small and negatively charged. An electron is actually 2,000 times smaller than a proton, which is ridiculous because all of this stuff is just absolutely tiny. And then we have neutrons, which are large and electrically neutral. So neutrons, neutral. When we look at mass number, we add, let me get back up there. When we look at mass number, like I said a second ago, we add protons and neutrons. We don't add electrons because they are so small, they don't really influence the atom's mass and indent. So we just focus on adding the protons and the neutrons for the mass number, for the atomic mass. See, most atoms have protons and neutrons packed tightly into the nucleus. So the protons and neutrons are packed tight, and then the electrons are floating way outside. The nucleus is the atom's core. We also have a nucleus in cells, which is the core of a cell. So that's all the nucleus is referring to as the center. The electrons orbit the nucleus. So yeah, the electrons are going to be way spaced out. So here's another pictorial of that. Elements differ in the number of subatomic particles in their atoms, number of protons. The atomic number determines which element it is, which we just talked about. Atom's mass number is protons, neutrons, and then mass is a measure of the amount of matter in an object. So let's move on to isotopes. Isotopes are different variations of the same element. Here you can see that the neutrons are differing between these different types of carbon. So these different isotopes of carbon. This is carbon-12. This is the one we were talking about earlier. So its mass number is 6, or its mass number is 12. It has 6 protons, 6 neutrons, and then it has 6 electrons. And then if you look at carbon-13, the neutrons are what differ, and then carbon-14, neutrons differ again. So 6 plus 7 is 13, 6 plus 8 is 14. radioactive isotopes. Okay, these are pretty cool. If you watch inactive elements, they'll give off neutrons very slowly. When they do that, they become radioactive, essentially. So they release radioactivity. An example of this is PET scans. So here, this person got radioactive glucose, and some of the carbons in that glucose, so remember glucose is C6H12O6, some of the carbons are radioactive. They're used to measure activity, so the parts of your brain using the most glucose will be the ones that are the most active, which are the ones that light up. This is used a lot with tumors, because if there was a tumor in this person's brain, it would show a lot. It would just light up white. It would show a lot of activity. Alright, so electron arrangements. They fill shells. Electrons fill shells in specific order, and they want to have a full outer shell. So let's see. Electrons orbit the nucleus of an atom in specific electron shells, and they want to have all these shells filled. Alright, so electrons, they're found around atoms predictably. So 2 will be in the first shell, and then 8 will be on the second and third shells. What does this mean? The best way to talk about it is just by showing you a picture. They're found in predictable locations. The inner shells are always completely filled first, and then we move on to the outer shells. So, here we go. Pictures. I like pictures. So an unreacted atom will have the same number of protons and electrons. Hydrogen, over here, you can see it has one empty space. So that means it wants to share electrons with other atoms because it wants to fill that up. And remember we said 2 are in that first circle, so the innermost shell. You can see the pattern of 2 in all these innermost shells. And then if you look at the outermost shell in each, there are 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8. Outermost shell, 8. So anyways, this little hydrogen has an atomic number of 1, and it has only an innermost shell with 1 empty. We move on to the carbon, and you can see that the innermost shell is filled, but the outermost shell, it can hold 8 electrons, but only 4 are filled. So it has these 4 little empty spaces. So these 4 empty spaces means that 4 bonds can happen, and that determines the types of molecules that can be made. So carbon can make a lot of different types of molecules. Nitrogen, 3 out of 8 are open, and then oxygen, 2 out of the 8 are open. So the goal of all atoms is to have outer electrons full, which is what we just talked about. Helium is one that is stable. Its outer electrons are full. So we call that a noble gas, which is going to be that last column on the periodic table. Let's move on to ionic bonds. So this is the first type of bond that we're going to talk about. Let's get all those up there. This is the first type of bond that we can make. Everything else we'll want to do a reaction. So here we have Na, which is sodium, and we have Cl, which is chlorine. So in sodium, we have this third outer shell. So we have an inner shell, a middle shell, and an outer shell. Well, remember, anything except for the inner shell can have 8 little spaces filled up. This one only has 1. So the outer shell can either lose 1 electron or gain 7 to fill it up. So losing 1 would definitely be easier than gaining 7 different ones to fill it up. So what does the sodium do? It loses 1 to bond with the chlorine, because as you can see, the chlorine has 7 out of 8 filled. So same here, it can fill in 1 or it can lose 7. Obviously the answer would be it'd be easier to gain 1 than to lose 7, right? Right. So what happens here is the sodium atom gives 1 electron to the chlorine, and now they're bonded together. So now they both have complete outer shells. Sodium's second shell here is filled, and chlorine's third shell here is filled. And now they've bonded together. So because sodium lost an electron, here you can see there are no charges, right? NaCl, no charges. Here you can see Na plus, Cl minus. So sodium lost an electron and became more positive because it got rid of 1 negative. So if you lose a negative, you become more positive. This is a life lesson too. Lose negative people in your life, become a more positive person. I'm just kidding. But anyways, and chlorine became more negative because it gained an electron from the sodium. So you added a negative, became more negative. You lost a negative, became more positive. So the positive is now attracted to that negative, and we get this ionic bond. We have sodium chloride, NaCl. And these ions are now called charged particles. So Na plus, charged particle, Ca minus, charged particle. Sodium ion, chloride ion. There we go. So let's move on. So covalent bonds, covalent means sharing. Here you can see hydrogen has 1 pair sharing, oxygen shares 2 pairs, and then if we move down here to water, we see that some interesting sharing happening here in water with an interesting shape, right? These 2 atoms, they don't share electrons very evenly. Oxygen is actually electronegative. It's an electron sucker, which will make it a little bit negative. And this is important to look at later when we talk about how important water is to life. So I'll talk about that more here shortly. Let's move on to hydrogen bonds. So hydrogen bonds are the weakest bonds, and they are formed between water molecules. So within water, we have covalent bonds, right? Covalent bonds hold hydrogen to the oxygen, the hydrogens to the oxygen, right? But between different water molecules, we have hydrogen bonds. So this is what forms lakes and rivers and the water in your bathtub. Again, this is based on unequal sharing that we just looked at, but if you have them in high numbers, they can be quite strong and add to surface tension in water. So hydrogen bonds are why it hurts so badly if you do a belly flop. Now let's move on to some chemical reactions. So we have chemical reactions with reactants and products. So cells constantly rearrange molecules by breaking existing chemical bonds and forming new ones. What does this mean? That means math is happening. We have reactants, so what goes in, what you start with, hydrogen gas, oxygen gas here. And then we have our products, what we end up with. So with these reactants, we end up with water, 2 molecules of water specifically in this example. So this just reiterates what I just said. On the left side of the equation are the reactants, the starting materials. So blank plus blank. Then on the right side of the equation are the products, the end materials. So this is the equals blank part. Important, chemical reactions cannot create or destroy matter, they just rearrange it. So moving on to water and life. Water is the most important thing ever. Without it, life as we know it wouldn't be possible. And life on Earth began in water and evolved there for 3 billion years. So think about that. We talked about 30 million in our previous chapter. Think about how much 3 billion is. It's just an astronomical amount. Modern life still remains tied to water. You can't deny that. And then your cells are actually composed of 70% to 95% water. So if anybody has watched the first X-Men where the guy liquefies, it's not too far off from being a possibility. albeit a terrifying possibility and very science fictionally a possibility. But anyways, moving on. Water is what makes Earth livable for us, honestly. And look at this. Look at this beautiful Earth with this beautiful water. All right, moving on. Structure of water. So we have oxygen covalently bonded to hydrogen and vice versa. And we have electrons moving back and forth between the two, but remember, it's not shared equally. Electrons are more likely to circle oxygen because it's a little bit of an electron hog. So whenever you have different charges, you have polar molecules. Water being a polar molecule is extremely important. Oh, let's move back. Okay, so between water molecules, we have hydrogen bonds. So this is a water molecule. Mickey Mouse, you see Mickey Mouse, it's a water molecule. So between all these water molecules, we have hydrogen bonds. Within the water molecule, we have covalent bonds. So these are the covalent bonds. And holding all these little Mickey Mouse ears, all these different Mickey Mouse ears together are hydrogen bonds, which gives us bodies of water. So the polarity of water is very important when it comes to water's cohesive nature, its ability to moderate temperature, ice floating, because imagine if ice didn't float, how strange would that be? And then the versatility of water as a solvent. So I'm going to break all these down and talk about them individually. So the cohesion of water. Hydrogen bonds are attracted to each other. Water molecules stick together because of these hydrogen bonds, and that's called cohesion. This is super important for water transport in plants and what allows roots and shoots to just absorb all that water from the ground and bring it up into its leaves, for example, with this tree. Then we have surface tension. This is a water strider, and it's able to float on top of this water because it distributes its weight out, and hydrogen bonds allow it to. So again, these hydrogen bonds are why it hurts so bad if you belly flop into water. Then we have how water moderates temperature. In order to change the temperature of water, a lot of heat has to be put in it. Water changes temperature very, very slowly. And because water changes temperature very slowly, it helps us maintain our homeostasis. Imagine if water didn't, remember we're, 75 to 95 or 75 to 90% water. Imagine if our water temperature, or if our temperature changed quickly. That means if we got slightly cold, we'd be freezing. If we got slightly warm, we'd be just perspiring ridiculously. But because water temperature doesn't change very quickly, it helps us maintain our homeostasis. Think about lakes. If it's a really, really hot day in early summer, the lake is still going to be cold. Like, it hasn't had enough time to warm up, right? The higher the temperature of water, the faster the molecules are moving. The lower the temperature, the slower they're moving. But I'll get into that in a second. So when we sweat, it's called evaporative cooling, and it removes heat from us. It allows us to maintain our body temperature. So let's move on to ice floating. So when water molecules get cold, they move apart, forming ice. A chunk of ice has fewer molecules than an equal volume of liquid water. This is the best way to depict that. Basically, water molecules and liquid water, you can see how close they are together. Whenever it gets cold, the molecules slow down, they spread apart, they form this crystalline structure, and it freezes, and that's why ice floats. If ice didn't float, we would be in trouble. This is really important for, big bodies of water, even small bodies of water, but, think about ponds and lakes and oceans. Water's always cycling, so if it gets too cold, that water that freezes goes to the top, and so it allows anything below it to still live without the fear of freezing, like little creatures or in lakes and definitely in oceans. Actually, there are some fish in Arctic regions that can make their own antifreeze, but that is definitely not common. I just wanted to give you guys a little fun fact. So, since ice floats, none of this freezes solid. Imagine if the ocean froze solid. Oh my gosh. That'd be horrible. Nothing could survive. So moving on to water as the solvent of life. Lots of things dissolve in water, different things like salt and sugar, and that gives us a solution or a mixture where everything is distributed. Blood plasma is another example. Cell fluid that we touched on in the previous chapter is one, and this is all based on water properties. So in this example, salt is the solute and water is the solvent. Together, you mix it all up. So put a spoon in, mix it really, really well, you get a solution. So a solvent plus a solute equals a solution. When water is a solvent, the result is an aqueous solution. So aqueous, aqua, you can say aqueous if that helps you remember it. Doesn't matter, it's like tomato, tomato, except it's tomato. Alright, acids, bases, and pH. So an acid donates hydrogen ions to solutions. So remember, these are charged. So you see H plus, it's charged. H plus charged makes it an ion. So hydrogen ions with acids dissolve off and go into water. With bases, the opposite happens. The base takes hydrogen from water and it basically takes it out of the solution. The easiest way to talk about this is by looking at a picture. Pictures are great. So this is a pH scale. You can notice that the bigger the number, the more basic the solution, the less hydrogen ions. The lower the number, the more acidic the solution, the more hydrogen ions, these little H pluses. This pH scale is an inverse logarithm, which just means the more hydrogen ions, the lower the pH. And as pH goes up, number of hydrogen ions goes down. So pH up, hydrogen ions goes down, as you can see here. And then you see 7 is human blood, pure water. This is our neutral zone. 7 is our neutral zone. So if we jump from a pH of 7 to a pH of 6, it doesn't seem that much, right? However, this pH of 6 has 10 times more hydrogen ions than pH of 7. We move down to 5, from 7 to 5, we get 10 times 10, so that's 100 times. So a little change in pH is actually a large change in acidity or, basic solution. And then we get to buffers. Buffers resist pH change. They are usually weak acids or bases. So if you add an acid, it takes up hydrogen ions. If you add a base, it gives up hydrogen ions. This is important, super important. If our body didn't have buffers and we drank orange juice, we could alter our red blood cells and their oxygen carrying capabilities. It's crazy. Just like these little changes that are so important for our body to function. Alright, so that is the end of chapter 2, which means you are ready for the chapter 1 and 2 quiz. That's due by Sunday at 11:59 p.m. Alright, talk to you guys later.